fundamental counting principle. You can use the counting principle to find the total number of outcomes. So the fundamental counting principle is literally something that you can do to calculate how many outcomes there are instead of making a tree diagram. So let's start with number one. Let me fill in these notes. If one activity can occur in, let's say, X ways, so X number of ways, and another activity can occur in Y ways, then both activities can occur in X times Y ways. All right, number one. To leave her office, Karen can choose between 3 sets of stairs, so that's our first number of ways, and 7 doors, that's our second number of ways. How many ways can she leave her office? So you just do 3 times 7. All right, I'm going to skip all the even ones. You can do the even ones on your own. Number 3, a class has 11 boys and 16 girls. How many ways can the teacher choose 1 boy and 1 girl? So just multiply and you get 176. Okay, number 5, a card is chosen from a standard deck. So that's the first thing. And we know there's 52 cards in a standard deck. Then a die is rolled. We know there's 6 sides on a die. How many outcomes are possible? So we're just going to multiply, and we get 312. All right, number 7, a day of the week is chosen. So a day of the week, there are 7 days in a week. And then a spinner to the left is spun twice. So this spinner to the left has 12 spots. If you counted all of these up, then you would get 12. So that would be times 12, and it's spun twice. So we do another 12. And pull up my calculator real quick. All right, so we got 84 times 12, and that's 1,008. So that many outcomes, 1,008 different outcomes. Number 9, a quiz contains 5 multiple choice questions. So there's 5 questions. Now normally I think this one's a little different. It's the same idea, but we're going to treat these 5 questions like 5 different items. So the first question has 4 answer choices. The second question has 4 answer choices, and so on. So all 5 questions have 4 answer choices. Good gravy. So I'm going to do 4 to the 5th power. I'll just use the TI Inspire app. And we get 1,024. Okay, so that's 1,024 different ways this could be answered. All right, the library codes their books using 2 letters followed by a digit 0 through 9. So we have 2 letters and a digit. How many different codes are possible? So the first letter, you have 26 choices. The second letter, you have 26 choices. And then the third thing is a digit. So that would be 10 different choices because you have 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10 different numbers you can possibly use there. Okay, and so that will be 6,760. That's a lot of different ways. All right, I'm supposed to do number 10. Oh well. All right, number 11. Patrick is buying a new car. He can choose the body style, color, and engine type. So I'll write that down. We got the body style, color, and then the engine type. If there are 54 ways he can select a car with 3 body styles and 2 engine choices, how many colors? So it says how many colors. We don't know how many colors. That's why it's asking us how many colors. But we do know that there's 3 body styles. That's a question mark, not a weird looking 2. And then we know that there's 2 engine choices and 54 ways that are possible. So 54 total possibilities. And now we got to figure out what that missing number is. So 3 times what times 2 equals 54? Let's just multiply the 3 and the 2 to get 6. And then we're just going to divide 54 by 6. Okay, we get 9. And all right, so there's 9 different colors that Patrick can choose from. Okay, number 13, a coin is tossed 3 times. What's the probability of getting heads just once? Now, I want to tie this lesson into the tree diagrams lesson. So I want us to kind of think about all the different possibilities. All right, so if we toss it the first time, that'll be heads, tails. If we toss it the second time, that'll be heads, tails. For heads, heads, tails for tails. So basically what I'm saying is you could have heads first, then heads second. You can have heads first, then tails second. You can have tails first, then heads second. You could have tails first and tails again second. All right, so that was the first and the second toss. Now the third toss, you could have heads, heads, heads. Or you could have heads, heads, tails. You could have heads, tails, heads. Or you could have heads, tails, tails. You could also have tails, heads, heads. You could have tails, heads, tails. You could have tails, tails, heads. Or you could have tails, tails, tails. Okay, that was a lot. I know it was a lot. I'm so sorry. That it was so much. Okay, I'm going to shrink that down so I can write. Okay, so that gives us a list of all the possibilities. And I'm going to write this in list format to make it a little bit easier for you. So again, we could have heads, heads, heads. That's this one right here. We could have heads, heads, tails. Okay, so that's that one, that one. All right, so we could have heads, tails, heads. We could have heads, tails, tails. We could have heads, oh, I'm sorry, we could have tails, heads, heads. We could have tails, heads, tails. We could have tails, tails, heads. And we could have tails, tails, tails. Okay, so that's all 8 of our options for doing 3 coin tosses. And it says, what's the probability of getting heads just once? Well, let's see. I see heads just once here. It's just 1 heads. I see another one here, just 1 heads, and 1 right there, and that's it. There's only 3 that have heads only once, so that's 3 out of 8. So the answer is 3 out of 8. Now, that's the long way, okay? Or that's like the longer way, I guess. Now, if you want to try it the way we just did it with the fundamental counting principle, I'm going to do it over here in a different color because why not? Okay, so if I did that, then I would just be like, oh, well, I have 3 coin tosses. I know coins is heads or tails, so that's 2 options. So I got 2 options for the first flip, 2 options for the second flip, 2 options for the third flip. So I got a total of 8 possible outcomes, which is the denominator. Also, you would have to figure out how many of those options just have heads once. So you know, at that point you have to be like, oh, I can do heads, tails, 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 heads, tails, or tails, tails, heads. You just have to figure that part out, and that would be still 3 options that go there. Okay, so yeah. All right, number 15. A card from a standard deck of cards is chosen at random. So we know we're going to have to use that 52. Then a coin is tossed. What's the probability of getting an ace and a tails? Okay, so I'm not making a tree diagram for this because we got 52 things we would have to do. We would have to be like ace, 2, 3, you know, all the way to jack, queen, and king. And then you still have to do a coin toss. You still have to do heads, tails, heads, tails. You know what I'm saying? That'll be a lot of writing. We don't want to do all that, so that's why we use the fundamental counting principle. And so we would just be like, oh, instead of doing 52 and then splitting it up into heads and tails, just do 52 times 2. You know, 2 options. 1 for the heads, 1 for the tails. Come on. Stylus is acting crazy. All right, and then that would be, what is that, 104? Okay. So that's our total. So that's going to go in the denominator. Okay, what is the probability of getting an ace and a tails? So how many options are there for ace and tails? Well, again, if I went with my whole ace, 2, 3, 4, dot, 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 jack, queen, king, and if I broke that into heads and tails, you know what I'm saying? And if I'm gonna just kind of finish this up real quick. So I'm gonna duplicate that, boom, duplicate that, boom. Just trying to give y'all an idea without me having to do 52 of these. Okay, so there's only one option that has ace and heads, and that's this option right there. So that would be 1 out of 52. I'm sorry, 1 out of 104. Okay. All right, number 17. All right, so we got these two spinners. What is the probability of getting yellow and an even number? So again, we can make a table. I mean, not a table. We can do a tree diagram, and I'm going to demonstrate both because I want you to see both. So we have yellow, orange, red. Oh my goodness. Blue and green. So we have all those different choices, and then for each choice we have 1 through 8. Oh Lord have mercy, what did I get myself into? So we got 1, 2, 3, 4, 5, 6, 7, 8. And darest I even put these numbers? Why am I doing this to myself? Who knows? I'm going to copy and paste it though. I can tell you that much. Okay, there we go. Or duplicate it, whatever. You get my point. I'm going to spread this out a little bit more because there's no way. I apologize for the jankiness. Okay, just rock with me for a minute. Okay, so I'll put the G down there, the B right there, the R over here, and I'll scoot the O over there. All right, cool beans. So that is my tree diagram. Got a lot going on. And we want a yellow and an even number. So yellow and even. I'll use yellow. All right, so that's going to be this one, this one, this one, this one. So that's going to be yellow 2, yellow 4, yellow 6, yellow 8. So that's 4 options. And then the total number of options, well, it's 8 for each one of those colors. So that's 8 times 5, which is 40. So that'll simplify to 1 over 10. Okay, and that would be the long way, right? Now the shorter way, I'll use pink. So the shorter way would just be to be like, oh, okay, well this one has 5 choices, this one has 8 choices. So if I use the fundamental counting principle, I know 5 times 8 is going to give me the total number of options, the total number of possible outcomes, and then I know that there are 4 even numbers here because I got 1, 2, 3, and 4. And for yellow, that would just be 4 because that's just one color, and then you would still figure out that it's this. Oh, sorry, that arrow was janky. You would still figure out that it was this. Okay, so that's why the fundamental counting principle is so helpful. But I like to do the tree diagram because sometimes I don't feel very comfortable just multiplying stuff if I can't see what it means, if that makes sense. All right, oh Lord, sorry. All right.